today we are going for our 11th lecture of the series. So last time we had started with the notion of a vector space. So we'll build upon that and we'll see what all things we can say about it. Most of it will be, you will see in another course. But the idea of a vector space is to use the tools we have developed so far on a set which will kind of behave like vectors. So what I mean by that is, suppose I have a set V with some bunch of objects, we will call them as vectors. So suppose we give a way to have an addition function or an addition operation defined on these objects. So that means if I have two objects in this setting, let me call them as U and W, then I'm telling that there is a way to combine these two objects, which I'm calling as addition. And if it so happens that U plus W also belongs to V, for every possible U and W, then we will say the set is closed under this operation. So we will call it as V is closed under vector addition. So imagine I am being given a set of objects with some operation defined on it, and if V is closed under addition, and let us have another operation defined on it, which is basically a scalar being multiplied to a vector. So when I say scalar, scalar means a constant which would be taken from a field. Usually we will be dealing with reals or complex. So think of it as being picked from either the reals or the complex. But in general it could be of any field. And this guy has been picked up from the vector space V. So we are saying for any scalar C and any vector U, let me just keep having a notation, C times U also belongs to the same set V. Then we will say the set is closed under multiplication by a scalar. So suppose I have a set which is closed under multiplication by a scalar, which is closed under addition among vectors, and it has a bunch of other properties which we will go one by one. And it has something called a zero element. What it means is that I have an object in this set such that if I take that object and perform an addition to any of my objects, I will recover my object. So this guy is acting like what 0 acts as in numbers. So we will call this as the zero element. Now another thing I want out of this is the so-called additive inverses. In other words, suppose I have this thing that for every vector in V, there exists a vector, let me call it as, let me give it some name, let's say call it M. There exists a vector M in E such that u plus m is the same as m plus m plus u, and it gives me the so-called the zero vector. Then we will say that u has an additive inverse. So right now it is very abstract the way I have written things, and it seems a bit haphazard also, because I want to develop these properties and show you how do these properties behave in a given set. So imagine if we had these properties in a set. I have defined two things, an addition and a multiplication by a scalar. We are saying it is closed under addition, we are saying it is closed under multiplication by a scalar, and it has an element called a zero element, which when added to any element preserves the structure of your element. And then I have a concept of additive inverses. For everything, every object in V, there exists another counterpart in V, such that the sum of those two objects in any manner gives you back the zero element. If we have such a setting, then we claim that we will have the beginning of what we call as a vector space. Now there are other rules also which I have not mentioned here, which we will bring in one at a time. But first let us see, are there sets and are there objects which have this kind of a structure, the 4 points that I have written over here. Do they have such a thing going on somewhere? Okay. So I'll take some cases and we'll see. So closure under addition, closure under multiplication by a scalar, the so-called zero element or zero vector, and the additive inverse. Now, I'll go through some spaces which we are more familiar with. So let us see, let's do a mental check. If I take an n-dimensional vector, if I take two n-dimensional vectors, if I add them, I'll still get a n-dimensional vector. So it is closed under addition, it is closed under multiplication by a scalar. Here I'm using that definition which we are familiar with. There is something called a zero vector, namely the vector, let me write it as a row instead of a column. Let's say some space. And for every vector u, which we call as u1, u2, un, the vector which will act as its additive inverse would be minus u1 which would be minus u1 minus u2 minus un. So at least in this familiar setting, we know that we have such a situation where all these four things we can find. But let us go to a slightly less familiar settings. Let's go with polynomials of degree less than or equal to 3 in X. There is no standard notation for this, I'm just making my own notation. So we are going for polynomials of degree less than or equal to 3, for example. If I take two polynomials whose degree is no more than 3, and when I say polynomials, these are polynomials over real numbers. So if I take two polynomials of degree less than or equal to 3, the resulting polynomial cannot have degree more than 3. If I take a polynomial multiplied by a scalar, the new polynomial will not have degree more than 3. The so-called zero polynomial will act as my zero vector. And for every polynomial of the form ax cubed plus bx squared plus cx plus d, if this is my polynomial p, I can say I have a additive inverse of that as the negative of this polynomial. So we do have the concept of an additive inverse. Now, what else can I go for? Think of this space, a space of continuous functions. So this is the space of continuous functions on the interval 0, 1. So any function that you can dream of on the interval 0, 1, which is continuous, has been put in that. Now I define addition and multiplication the regular way. How do you add two functions? You add them pointwise. How do you multiply a function by a scalar? You scale it pointwise. So if I take two continuous functions from your calculus, you would have seen sum of two continuous functions is continuous. If I take a continuous function multiplied by a scalar, it is still continuous. The 0 function, f of x equal to 0, is your 0 vector. And for every function f of x, there is a counterpart minus f of x, which is also continuous. And the sum of these two guys will give you the 0 function. So what we are seeing is these are very different worlds, but they seem to have some kind of a common structure, common algebraic structure, if I may say, which is shared by all these worlds. In fact, if you think, these are so different. Out here there are uncountably many functions over here. Out there are uncountably many vectors. But in here there's a geometry which you may not find it so in an obvious manner in the other spaces. But they seem to have something which they all share, and which is this common way of looking at things. By the way, these are not the only examples that you can come up with. There are other examples also where things are kind of different. So for example, we can come up with a weird example. Let's try and see if we can. Although maybe that can wait for some time. Let's not make it more complicated than necessary at this stage. What else? Let's try to see. What about another space? So here's my space of all n by n matrices over the set of real numbers. So all square matrices with real entries. If I take any two such matrices, as we have seen under matrix addition, the sum of two n by n matrices will be sum n by n matrix. So it is closed under addition. If I scale each and every entry by the same scalar, it is still an n by n matrix. The so-called zero matrix is going to act as the zero element. And for every matrix A, we have minus A as its additive inverse. So we do see that among the set of matrices also, we can have this kind of a structure. So for us, all these sets with their operations, we will treat them as vector spaces. That means they all fit this kind of a bill. And we try to understand the structure. So instead of going through each and every space once, what we will do is we will try to develop tools for a general setting, and then we will apply them on each of those spaces as the need arises. Okay? So let's take it from here and see what other things I need to add. There's one thing that should have come by now for us, that I haven't defined any kind of relationship between the addition and the multiplication, in the sense, how do they interact with each other? So there are rules for that. I will list some of the rules over here, and the rest you should be able to get from your textbook, just to give you an idea how the addition interacts with the multiplication. But before I do that, let's try to see some examples which look very similar in the nature of what we have done, but may have some little bit of a difference. Suppose here is my set S. And let us say I define this set S as AX as degree 3. So it is the space of all polynomials with degree 3, and the coefficients are real numbers. Is it a vector space? under addition and multiplication the way we have defined it. So for example, will it be closed under addition? So for example, if I take 3x cubed and add 2x cubed minus 7, I will get 5x cubed minus 7. So this guy still belongs to S. So the sum of two things does belong to S, but will it be true for all the elements? So for example, if I had taken 3x cubed and minus 3x cubed, it gives me 0. And definitely this is not a polynomial of degree 2. So would you agree that this is not really closed under addition, and hence it is not a vector space? Okay. Likewise, if you look at the interval 0, 1, suppose instead of looking at the real numbers, I confine my focus to just 0, 1. So all elements A which lie in the interval 0, 1. And we are going with regular addition and multiplication. Then this is not a vector space, because if you take 1/2 plus 3/4, which will give you 5/4, which does not belong to T. So you started with two objects which were in T, but the sum of those objects is not in T, and hence it is not a vector space. So keep both kind of examples in mind, and this will help you understand the concept a little more better. Let me try to introduce one more thing before we go with the full aspect of general vector space. Let's see if we can take it one notch higher. Remember the solution set? Remember, well, let me first recall. Remember this homogeneous system? Then we talked about the solution set of this homogeneous system. So let me call the solution set as S, to be all those vectors in Rn such that Ax is 0. So basically the solution set of this homogeneous equation. Those of us who want to make a difference between the variable like this, let's put Ax 0. So all the solutions of this guy. I claim that the solution set also follows this structure. So for example, let U and V be in S. Then I claim that their sum must be in S. So if I want the sum to be in S, it means what? I have to show you that this guy will turn out to be a solution for the homogeneous system. So let us look at it, what it does to the vector U plus V. This is AU plus AV. Now U is in S, hence it is a solution of the homogeneous system. V is in S, so it is also a solution of the homogeneous system. So that way we can now claim that U plus V is also in S. And by very similar reasoning, it can be shown that C times U will also be in S for every real number R. So this is something you can try to prove on your own. So what this tells me is that at least whatever the solution set is, this world is closed under addition, it is closed under multiplication by a scalar. And what about the so-called zero element? Let's talk about the zero element. Remember, there is a criteria that we have to fit. We can't simply just say, oh, well, it's going to be the zero vector. We have to make sure that whatever vector we are claiming as zero element must be a solution to this system. And it so happens that the zero vector is by default a solution to our homogeneous system. So that way we are sure that the zero vector will play the role of the zero element. And likewise, if you have U as a solution, then A times minus U will also be a solution to this system, and you can check that this guy will act as additive inverse. So we have the full thing that we saw in other spaces. So it seems that this guy is also going to be looking like a vector space to us. Something worth noting, because we will use it very soon. We'll call this space as the null space. But anyways, let's not get worried about those definitions yet. My objective was to show you that things we have seen before can also behave like a vector space. Okay, so let me now show you how to make these things interact with each other. There's one more requirement which kind of I've used it without mentioning it. That requirement is that the vector addition is commutative. So for all u and v, u plus v will be the same as v plus u. Then we want to deal with associativity. So vector addition is associative also. So what we mean by that is, it doesn't matter how we group these addition and these vectors, they can be added in any order. So vector addition is basically associative, commutative, it is closed and all that. So what is the link between multiplication? Well, let's see if we can come up with links between multiplication and addition. First things first. Suppose I have scalars C and D. Let me say they are real numbers. Then C times the vector D is the same as CD times the vector U. Okay. Now let me go with the interaction of a scalar with vector addition. So how does the scalar multiplication or the multiplication by a scalar deals with this vector addition? So these are some of the natural properties that we kind of see in other scenarios. And we're just saying that this is exactly how we will have things worked out for us. So in some sense, this multiplication by scalars is distributive. Multiplication of a vector by the sum of the scalars is basically multiplying the vector by each of those scalars and adding it up. So these are like some of the properties that we will have. There's a list of about 10 or 11 of them. Well, I have written almost 9 of them already. So the remaining 2 you can see. And whatever space satisfies all these axioms, we will call that as the vector space. So that would be the general way of looking at vector space. Now we'll go about proving, we'll go about seeing more structure into these things a little later on. But I want to right away deal with one thing, which we will call as the subspace. Okay, what is a subspace? Well, suppose I have a set which is sitting inside my vector space. Suppose this set is non-empty and S is a vector space So S is a vector space in its own right with the operations of V. What it means is that we have this world V in which we are looking at a subset of V. And we are saying that this guy behaves as a vector space on its own. So if I take two things in here, then their addition is going to be in the same space S. Okay? And same thing with vector multiplication by a scalar. Now the question is, do I have to really go through this entire list to claim something is a subspace, or can I basically cut things short? The simple answer is that we only need to check few things in this list, and that can guarantee us that if something is a subspace. So firstly, let us see what things I need to check. I need to check it whether the space is closed under addition or not. So these are the checks that I'm going to perform. Is S closed under addition? The second thing I'm going to check is S closed under multiplication. Question is, are these two enough to guarantee me that it will behave like a vector space? Now let us look at these guys. What about the zero element? Could it happen that the zero element of this guy will be different from the zero element of S? See, if that was true, then this would have some problem with the zero element of V, because then for some vectors of V, we may have more than one zero element. So in some sense, I'm kind of assuming without proof that the zero element of the vector space V is unique if it exists. Unfortunately, those proofs we will have to skip for now, because they will be part of what we call as linear 2. So right now you have to take this for as my word that the zero element will be unique. Although the proof is not difficult, it can be done, but for the sake of time, I'm skipping it. So zero element is something that we will get for free if it is a subspace, and if I can guarantee that it is non-empty. What about the additive inverses? Well, I claim that existence of inverse can be taken care of if I know that it is closed under addition and it is closed under scalar multiplication. And all these properties, these were not the properties of the set, they were properties of the operations. So if these properties are holding true in the larger vector space V, they will also hold true in the smaller subspace S. Okay. So let's focus on subspaces a bit more, and then we'll worry about the vector space structure in general. Okay. So first things first. Suppose I have the zero vector in my vector space. Is this a subspace? Is the so-called zero set a subspace of my vector space? Well, the zero set will definitely be closed under addition. 0 plus 0 will give you 0. And any scalar times 0 will still be 0. So definitely this will be a subspace of any vector space. Likewise, by default, V is its own subspace. So these are the so-called trivial subspaces. So we are interested in things which might be non-trivial. So let us focus our attention to R2. Suppose I give you a set in R2. Let us say, for starters, let us say the x-axis. Is this a subspace of R2? Now, if I take this, look at this guy, zero vector. Definitely zero vector lives on the x-axis. So here's my set S, which is the set of all vectors in the x on the x-axis. So if I have this set, if I take any vector u, and then I take another vector, say v. Recall your vector addition. Can I say u plus v will still be on the x-axis? So if my vector u is of the form a0, if my vector v is of the form v0, then u plus v would be simply a plus b0. And as you can see, it still belongs to S. So definitely this is closed under addition. What about scaling it? If I take u and multiply it by a scalar c, if c is positive, it will stretch the vector along the positive x-axis. If c is negative, it will bring it, but still on the x-axis. So c times u will be a vector ca0, which is still in S. So based on our check, we can definitely say that the x-axis will form a subspace of R2. Now, what about other subspaces? I found 3 subspaces of R2, namely the 0 subspace, entire R2, and now we are saying the x-axis is also a subspace. What about the y-axis? If I take the y-axis, will it form a subspace? Well, if you think whatever argument we did for the x-axis, the same argument can work for y-axis, because this time the first component is 0 and the second component could be non-zero. So it will pretty much behave like the way we have written over here. One thing you should see in common, in both the subspaces, this vector was common, namely the 0 vector. And 0 vector will always be part of any subspace. In fact, it's a very simple test. If your set does not have the 0 vector, or the so-called 0 element, then that set cannot be a subspace. So let's see a couple of examples. Of things which may or may not be subspaces. So let us look at this set. In R2, such that y is equal to minus 5x. Let's look at this guy W, which is all the vectors in R2, such that y is x plus 1. Now, question is which of these are subspaces, which of these are not. So we can go with the simple observation first, that both those sets are non-empty. The question is whether they'll be closed under addition and multiplication. So let's first talk about T. Is this a vector space? Is this a subspace? If you look at this, it's a line which passes through the origin, and we're saying y is equal to minus 5x. Okay, so say something like this. So at least one thing is for sure, that it has a 0 vector on it. So well, there's a chance that it could be a subspace. But if I take a point in here, can I say that the direction vector of this guy would be along this line? If I take another point in this set, the direction vector would be still along the line. So if I have two vectors which lie on the same line, then their sum would also lie on the same line. So we kind of hope that this will work out for us. But let us see how to formally test it. So for T, let let us say I have two things which belong to T. Then that means U must be of the form A5A and W would be of the form B5B for some real numbers A and B. Okay. Oh, I'm sorry, it should be minus 5A and minus 5B. Okay. Then what would be U plus W? U plus W would be A plus B minus 5 times A plus B. As you can see, the second component is minus 5 times the first component. So definitely this guy belongs to T. So it is closed under addition. Likewise, you can go with scalar multiplication. And this will give me AC minus 5 times AC. So again, the second component is minus 5 times the first component. So it is closed under multiplication. So what we see is that this qualifies as a subspace of R2, and it's a straight line which passes through the origin. What about the second guy, W? The second set, y is equal to x plus 1, will also be a straight line. And the kind of line it would be, it would be what? A line which goes like this, which will cut the x-axis at minus 1, and it will cut the y-axis at plus 1. So again, this is a straight line, which is nice. But if you make a quick observation, it is missing a vital component which could have made it a subspace, and that is the zero vector is lying over here. And remember, the zero vector would be there in every subspace because you need a zero element to act as the additive identity. So this is not a subspace. Because it does not have the zero vector. So one can say, okay, fine. If it doesn't have a zero vector, what if I supply the zero vector to it? That means what if I consider this space? What if I create a new set? Let me call this new set as F, which is W union the zero vector. Now problem, is it solved? That means now my set is this line and this vector. Will this be a subspace? So the question is the zero vector the only thing which was missing, or is it more to it that this thing is having a problem? So let's try to take it geometrically. If I take any point in here, then the vector corresponding to this would be like this. And if I take any different point over here, the vector corresponding to this would be over here. So if you do the sum of these two vectors, it will not be on this line, it will be outside the line. So the zero vector was not the only problem that it was facing. In fact, it is not even closed under addition. Just to give you a concrete example, let us take a look at this guy. So suppose I take x as 1, then y is 2. And let us say x is 2, then y is 3. Would you agree that these guys definitely belong to F? Because y is one more than the x. But what if I take the sum of these two guys? 1, 2 plus 2, 3. What if I take the sum? This will give me 3, 5. Now this guy definitely does not belong to F, because the y component is not one more than the x component. So it has gone out of the space. So 0 was not the only thing it was lacking. Even if I supplied 0, it is not basically closed under vector addition. Hence, it cannot be a subspace. So at this moment, one may ask a question, what are all the subspaces of R2? We have got at least 3 of them. And no, in fact, we have got 5 of them by now. the zero subspace, the entire R2, this is straight line y is equal to minus 5x, the x-axis and the y-axis. Are there more? Can we say every line that passes through the origin, every straight line that passes through the origin will be a subspace? And if yes, is that all, or are there going to be more? So that is a question we would like to answer. What exactly is a subspace, all the subspaces of R2? And in general, what will be the subspaces of Rn? So this is a question I would like you to ponder over for some time. Do I need to put it back to, or will it work? Will it work directly, or do I need to put it back and reset or something? Okay. So what are all? The subspaces of R. Here is our guess. R2, the zero subspace, and all lines passing through 0, 0. Okay. Now, I haven't technically shown you that all lines passing through 0, 0 will be a subspace, but if you look through the proof I gave for y is equal to minus 5x, the same proof can be extended for any straight line of the form y is equal to mx. So that way you should be able to convince yourself that at least we have these guys as subspaces. But question is, are these all, or are there more? And then the next question would be, what about R3 and Rn in general? What kind of subspaces will these guys have? So let's talk about R3 a little bit, and hopefully that will help us make a guess for Rn. So if I'm talking about in particular R3, what are the linear objects, if I may use that word, what are the linear objects you see in R3? Well, R3 will have lines. R3 can also have plane. So we have lines, we have planes. Lines we have seen kind of seem to work in R2. Will they work in R3? Perhaps they will. What about planes? Will planes be a subspace? So let's think of a plane. So let's think of a plane of the form x plus y plus z is equal to 0. Notice, I have chosen a plane which passes through the origin, so that at least I'm guaranteed that the 0 vector lies in my set. Is this something which is a subspace? Is S a subspace of R3? Now there are a bunch of ways in which we can answer. One of the ways I claim I have just shown you a little while ago. If you focus on this, the condition I have given, x plus y plus z equal to 0. Isn't it a homogeneous system? Well, it's kind of a misnomer to call it a system because it has only one equation, but well, let's keep with the terminology. It's a homogeneous system. And what did I show you a little while ago? That the solutions to the homogeneous system is actually a vector space. And S is nothing but the solution to this homogeneous system. So of course it is subspace. I could have used the same logic over here with my example over here, that it is a solution to a homogeneous system and hence it is a subspace. That's one way of looking at it. Another way of looking at it is as follows. Look at this guy. Can I say that this tells me that the dot product of these vectors is 0? So in some sense, this guy is a collection of all the vectors which are orthogonal to 1, 1, 1. So let's see if this is going to help us in some way. I'm just showing alternate ways of looking at the same thing, which can perhaps enhance our experience. So let's try and see. Here is so I'm saying that S, I'm just describing the same thing. S is the set of all those vectors W in R3 such that W dot 1, 1, 1 is 0. That means W is orthogonal to the vector 1, 1, 1. So for sure, the 0 vector belongs to S, because 0 vectors are orthogonal to everything. And let us say if I have two vectors u1 and u2 in S, then u1 plus u2 dotted with 1, 1, 1 will be u1 dot 1, 1, 1 plus u2 dot 1, 1, 1. And since u1 and u2 are in S, so this would be the 0 vector. So that means the sum of those two vectors which are orthogonal to the vector 1, 1, 1 will still be orthogonal to the vector 1, 1, 1, and hence it is closed under addition. And definitely we can check it for this other one also. If I take C times U1 and dotted with the vector 1, 1, 1, I can write it as C times U times or U dot 1, 1, 1, which is 0. So you can also say that this C times U1 is orthogonal to the vector 1, 1, 1, and hence it is in the set S. So under both the operations, the set S is closed, and hence set S is a subspace of R3. So if I take any one vector and anything orthogonal to that will be a subspace of R3. In fact, if you look at the proof, if I take a vector in R4 and take things which are orthogonal to that vector, whatever that object might be, that object according to the proof we have given will also turn out to be a subspace. And that is the reason I went through this way of looking at it rather than the usual way, because it has more potential of getting generalized. So if you were to take a guess about R3, what are all the subspaces of R3? Can we say it will be R3, it will be the 0 vector, all lines that are passing through the origin, all planes that are passing through the origin? Again, the question comes, are these all? How do we know that? So these things we will be able to better answer once we get into a concept of what we call as the basis. So that thing we are going to talk about next time. But I want to bring out some particular objects out of it. I'm going to talk about some particular spaces which are associated, which we want to deal with. In fact, let me do another example of something which is slightly different from usual things. Remember our polynomial space? So these are all polynomials. we convince ourselves that it has the vector space structure. So now I take polynomial, a subset of this polynomial, all those polynomials such that the constant term is 0. So all those polynomials in this space such that the constant term is 0. So things like x minus x cubed plus minus 7x plus 7x squared plus y times x square root of 2x squared, all these guys live in here. In fact, 0 polynomial also lives in here because, of course, the constant term is 0. All these guys are examples of things which live in S. Question is S a subspace? Or is S a subspace of R3? Oh, sorry, of P3. If it is okay, let me. Is S a subspace of P3? Well, let's see. If I have two polynomials in S, the reason they are in S is their constant terms must have been 0. That is the only reason they are in S. So what about the sum of the two polynomials? Now we are adding the polynomials the usual way we add. That means adding all the terms of the same degree together. So if you look at this, I call this polynomial as some Cx. I want to know what is the constant term of this guy. Well, if I evaluate this polynomial at 0, then this would be a0 plus b0, which we know is 0. So the constant term will still be 0. Hence the sum of these two polynomials will still be in the same set, and hence it is closed under addition. Same thing goes if I multiply the polynomial in S by any scalar, the constant term will still remain 0, and hence it is a subspace of P3. So what I'm trying to show you here is that the kind of structure we were observing over there is very similar to the kind of structure we are looking in other spaces also. And if I may take you a little bit on a joyride, if you look at any third degree polynomial, ax cubed plus bx squared plus cx plus d. Let me correct my statement. If you look at any polynomial that has degree less than or equal to 3, can we say it will look like this? Now what is the reason of doing all this? Well, we'll see. If you look at this guy, this polynomial, if you think in a particular way, the x cubed, the x squared, x, these are all placeholders. The real thing is about a, b, c, d, and that is what identifies this polynomial to me. So would you agree I can associate the so-called four-dimensional vector in R4 with any polynomial? So if that is the case, what is the set that I'm dealing with here? This set says the constant term must be 0. That means I'm looking for polynomials of the form ax cubed plus bx squared plus cx plus 0. So that means we are looking for a subset like this, a, b, c, 0. So we are saying things like that, whose fourth component is 0, will also be a subspace of R4. Okay? Now, why should we feel so great about this? Remember, this world is R4, and this world out here is we are saying the polynomials of degree less than or equal to 3 seem to be behaving almost like vectors in R4. So there is something called isomorphism, which we will unfortunately not be dealing with too much of it. But what I would want you to get from here is isomorphism in some senses when two things are going to behave in a same way apart from their differences on the surface. What I mean by that is, if you look at these two, these seem to be two different worlds, but the way they are behaving, addition, subtraction, multiplication, it just seems that they're having the same kind of algebraic operation going on with them. So it would be best to study a generic model, which we call as vector space, rather than getting confined to special sets like R4, P3. So our attempt is to create a general model which will fit all such examples.